Can I tell you, I did have one YouTube video that like hilarious. If I'd been monetized, I might have actually made like $30 from this thing. I had one YouTube video that exploded where Calford and I have made a bunch of apps for the school. Like when you guys, oh, you're welcome. Were any of you here that one semester where we were online and you had to like sign in your own attendance every day? Remember that stupid app? And that would like take you to class with thing. Yeah, I built that. You're welcome. And then I built the app that like they used to like book computers and stuff. And we built a few things like that. We built one for the resource room to use for like sending kids there and like keeping track of them, but then they decided not to use it. So we'd use a bunch of those. And it's this really kind of stupid platform called Power Apps, which is super clumsy. And if you're a real coder, which I am not, but Calford is, but I'm a real coder adjacent, you go into Power Apps and everything is backwards. Like everything you try to do is wrong. And one of the things in coding that you have to use a lot is like what's called a loop. In other words, you say like, okay, computer, do this thing until this thing happens. Does that make sense? So like, and think how often you use that even in your life, right? Like you don't even think about it, but like if you're sharpening your pencil, keep spinning it until the pencil is sharp, right? If you're driving, keep driving until you get somewhere. If you're turning around a corner, keep turning the wheel until the car is turning enough. And then keep it where it is until you need to straighten out, right? So the idea of do something until there's a reason to stop doing it's really important, right? Every coding language has this, except Power Apps, where there's literally just no such thing. You just can't do it. So I discovered this really stupid workaround where you could make like a graph and just put random, like just put the numbers, a table of values, and just put the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then say like, for each number in this table, do this thing, and then you could just put as many numbers in the table as you needed to do the thing. Ridiculous, like an absolutely stupid way of doing this. And then I was just talking on the phone with Calford trying to explain to him how to do this, and he's like, I'm not getting what you're saying, which makes perfect sense because I'm a terrible communicator, which is why I chose a life in teaching. So I just really quickly opened OBS and just recorded myself how to do this for loop in Power Apps. And then I just sent him the link. I said, like, just watch this. So it was like a 30-second video of me being like, yeah, you make the table and you put the numbers in it, and then you can use this command and it acts like a for loop. And I never thought about it. I only made the video to show Calford. And then like a month later, it was like, your video has like 400,000 views. And I'm like, what? And this is just a thing a lot of people were Googling, and like my video was the only one on there saying how to do it. So this video like exploded. And then they added for loops to Power Apps, and now my video is useless. But it was this funny thing where it was just like, that is the thing. And it was also me like peak COVID, right? So those days when I was wearing like boxer shorts and like a button-up shirt done up to here because the camera was only going to see me from there, and like in my sadness cave in front of my washing machine being like, all right, we're going to do chemistry today. How many people have logged in? Oh, 2? Oh, great. Okay. Hi, Richard and Hannah. We're going to do this thing. And then like next class be like, oh, hey, we're going to do grade 9 math. How many people have signed in? Oh, none? Okay. I guess I'll run the meeting and record it anyway. Yeah, so I was horribly sad. So it's also a video of me being like, yeah, Tim, so if you need to do the Power App, you just like, and like probably the dog was barking, but my kids were fighting. I was like, shut up. Anyway, that was a big hit. Anyway, let's get to it. So the basic idea was this. If we want to take chemistry and do it at the human level, instead of working in atomic mass units, which are tiny, we want to work in grams. Does that make sense? And really the point is, this is the relationship. This is counting. In other words, this is number of atoms, right? Whereas this is weight. The problem with this is, yeah, it's weight, but it's tiny. Does that make sense? And then this is a weight we can use. Does that make sense? So really, scientists just have to say, okay, the problem is chemistry is done with counting. This reaction doesn't tell me that 2 grams of magnesium react with 1 gram of oxygen to give me 2 grams of this. That doesn't even make sense. 2 grams plus 1 gram can't equal 2 grams, right? That doesn't make sense. Rather, what it tells us is that 2 of these actual atoms, you'd have to count them, react with 1 of these actual molecules, you'd have to count it, to give me 2 of these. You'd have to count them. Does that make sense? But we want to work with weights because we can't count atoms. Right? Does that make sense? So how do we go from counting to weight? Well, the answer is that we know how much everything weighs, right? So we know that magnesium weighs how much? Can somebody read it? I think that's 24.3. Is that right? Yeah. Okay, so we know that a magnesium atom weighs 24 atomic mass units. Does that make sense? So if I had 2 of them, how much would that weigh? Well, 24 plus 24 is So another way of saying this, if we wanted to, we could say 48 atomic mass units of magnesium, if we went and weighed that out, plus an oxygen stuck to an oxygen. Each oxygen weighs 16, but since we have two of them stuck to each other, that will be 16 plus 16 is 32 atomic mass units. And then this, well, actually, we know what this has to weigh, because even though we could work it out and say, okay, magnesium, remember the other day we looked at the molar mass of this, right? And we could say the molar mass of magnesium oxide is just, magnesium weighs how much? 24.3, right? And oxygen weighs 16.00, right? And so we could say one of these weighs 24 and 16, 20 and 10 is 30, 4 and 6 is 10, so that's 40.3, so 40.3 grams, right? But then how many of them do we have? Two. So what's 2 times 40? 80. And what's 2 times 3?
80.6.
Yeah, but you know, I'm just going to do the 80 because it occurs to me I didn't do any decimals there. Does that make sense? So we could look at the periodic table and figure out the weights of these. Does that make sense? Does that feel okay? Now here's the problem again. Am I going to weigh out 48 atomic mass units of magnesium and 32 atomic mass units of oxygen? No. And you know why I'm not? Because that's really tiny. But here's the thing. Now we know the weight ratio. Does that make sense? So if I could weigh out 48 atomic mass units and 32 atomic mass units and get 80 atomic mass units, when I scale this up so that instead of atomic mass units, I'm talking about grams, I actually know the ratio now. Does that make sense? It's going to be a lot more than 2 atoms. But if I get a big chunk of magnesium atoms, I could weigh out 48 grams of magnesium. And if I also weighed out 32 grams of oxygen gas, those should react perfectly. And when they do, how much magnesium oxide will I get? 80 grams. Does that make sense? So we're going to use the fact that we know their weights in atomic mass units and use that to figure out how much we should weigh out in grams. Does that make sense? And as it turns out, scientists were able to figure out how many, and again, why do we start with hydrogen? Hydrogen has the advantage of what does it weigh?
Just 1.
It weighs just 1. Does that make sense? Which makes it a great thing to start with. And what scientists were able to figure out is that 1 hydrogen atom weighs 1 atomic mass unit, which means 1,000 hydrogen atoms would weigh 1,000 atomic mass units. And then here's what they found out. That if you want 1 gram, if you want to count that out, all you have to do is get, ready for this? Very easy. 6, 0, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. That many hydrogen atoms. And if you do that, that will weigh 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23 atomic mass units. But as it happens, that many atomic mass units happens to weigh exactly 1 gram. Does that make sense? Now, a few points. 1, do we want to write that number like that?
No.
Now, that is clumsy. You know what this would be a really good time for? Scientific notation. Yeah, scientific notation is going to be a much better way to say this. As it happens, if you have 6.02, and this decimal keeps going, we're just going to stop there because that's fine, times 10 to the 23 hydrogen atoms, then that would weigh 6.02 times 10 to the 23 atomic mass units, right? Because again, how much does each hydrogen weigh? 1. Does that make sense? Now that's a really big number. That's a lot of atoms. That is 1,000 atoms for every star, or sorry, that's 1,000,000 atoms for every star in the universe. It's an insane number. And that is how much 1 gram of hydrogen weighs. So to get a gram of hydrogen, this is how many atoms it takes. I cannot stress to you how insanely big that number is. If you tried to count to that, if you got all 8 billion people on Earth to just count, it would take them 1,000 trillion years. And the universe has only been around for 13 billion years. In other words, if every living person on Earth attempted to count all the atoms in just 1 gram of hydrogen gas, They could not do it. A computer could not do it, not even close. All the computers on Earth wired together just to count all the hydrogen atoms, just to number them, not to do anything with them, just to number them. In 1 gram of hydrogen, we do not have enough computing power to do that, not by a long shot. In fact, those computers would have had to have been running for 1 billion lifetimes of the entire universe just to count all the atoms in 1 gram of hydrogen. Long story short, guys, atoms, real small. Real small. Does that make sense? But this number ends up being really important because what it means is we can take really tiny things and talk about them on the human scale. Does that make sense? We're never going to count atoms individually. So instead, we use a group. And remind me of other group numbers, counting numbers that we use in day-to-day life. When you buy donuts, we buy them by the dozen. When you get cents, which is the smallest unit of money, right? The smallest unit of money in Canada is a cent. But more often than not, we don't talk about cents. We group them in hundreds and we call those dollars. Does that make sense? Even that's a counting number, right? It's 100 of something. So here, this becomes our big counting number, and it's called Avogadro's number. Avogadro's number. It's named after a guy called Avogadro. If you had discovered it, it could be Roost's number. If I had discovered it, it could be Orlando's number, but it's not. It's Avogadro's number. Does it sound like avocado's number? Kind of. So we have a page for that. So we'll say this. 6.02 times 10 to the 23rd atomic mass units equals 1.0 grams. This is Avogadro's number. It's useful because we can use it to convert from number of atoms and that's what balanced equations used to mass. And of course, where do we use masses? Well, in the real world, right? Does that make sense? So the advantage of Avogadro's number is it lets us go from atomic mass units to grams, which means that if we know that we need 4 beryllium atoms, with this, we can actually figure out how many grams we need. Now, the good news is this. We are going to use this number for one day, just today, then we're never going to talk about it again. Because the whole reason we use this number is that it becomes invisible. Because the beautiful thing, 1 hydrogen atom weighs how many atomic mass units? One atomic mass unit, right? Which means this many of them would weigh one, what do we go to? Gram. Great. So this many nitrogen atoms, how much would that weigh? Nitrogen. And again, what's its mass? 14. So if you had this many nitrogen atoms, it would weigh 14. How much would this many gold atoms weigh? AU, number 79. If you had this many gold atoms, it would weigh 196.96, blah, 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 yeah. So like almost 200 grams. If you had this many mercury atoms, it would weigh 200 grams. Does that make sense? So today we're going to work with this number, but the beautiful thing, another thing we love about the periodic table, is once we're done today talking about why this is important, we don't really care about this number again. This number isn't important to work with. It's important that somebody else worked with it. Somebody else did the hard work of figuring this number out so that we don't have to. You know what we work with? The mass on the periodic table. And up till now, anytime you looked at the mass on the periodic table, you've always thought of that as atomic mass units. After today, every time you look at a mass on the periodic table, you're going to think of it in terms of grams. Does that make sense? From now on, when a chemical equation says, oh, we need 1 carbon, you're going to say, okay, that's cool. I need 12 carbon grams. I need 12 grams of carbon. Does that make sense? And if a chemical equation says we need 2 magnesium, you'll say, okay, no problem. Well, 1 magnesium weighs 24, so 2 magnesium weighs 48. Does that make sense? From now on, because somebody else figured this number out, we're going to read the periodic table in grams. Does that make sense? That's what this number does for us. Because if you have this many of any atom, its mass in grams is just the same as its mass in atomic mass units. Because that's how many atomic mass units make up 1 gram. It's a conversion factor. And because it's a counting number, like dozen, or like couple, or like pair, or like score, or like century, which is 100 of something, we need to, well, century actually isn't just 100 years. It's actually 100 anything. We use it for years. But of course, what did we call 100 soldiers in the Roman army? A century. What did we call the person who commanded them? A centurion. Not a good name. Wouldn't you like to be centurion? Isn't that a great title, though? Who are you? I'm the centurion. That sounds commanding. That's like serious business, right?
So like a cereal.
Right? So this is another counting number. And I can't stress enough, look at me. This is one of those things, often in life, the first time we teach you something, we teach you like, oh, this is why it works. And we do the confusing bit. And then going forward, you forget all the confusing bit and you just do it. Does that make sense? Like probably in cooking class, then here take culinary. Like the first day you take culinary, they're explaining to you like what a roux is and where it came from and like why it's called that and blah, 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 blah. And like all this stuff and it feels overwhelming. And then every day after that, they're just like, yeah, it's equal parts flour and oil, mix it together, heat it up and go. Right? And then like the first day you learn about julienning, you learn like where the name comes from and like its history and this, that. And after that, like, yeah, cut into thin stripes, go. This is kind of like that. Today's lesson, the stuff we do here, where we're counting individual atoms and working with really big numbers, is kind of confusing and stupid. And then from now on, every day after this, it's going to be really easy. So today is literally the worst this ever gets. Do you trust me on that? It actually is all easier than today. So if today you're kind of like, what is he talking about? Have a little faith in me, whether I've earned it or not, just give it to me. And just trust me that like going forward, this gets less confusing, not more, because it totally does. Because today we're kind of explaining why it works, which I think is important. I want you to hear why it works. But the truth is, if today goes over your head and it takes you some time to figure out why it works, tomorrow and the lessons after that, we explain to you how to use it. How it works, not why it works, but how. This is what we do. And how it works is actually really easy. Because again, what we do then is we look at the periodic table and we read that number, but instead of thinking of it as a little tiny atomic mass unit, we think of it as grams. And then we look at the balanced equation, and if it says we need 3 of something, then we take those grams and we multiply it by 3. And if the balanced equation says we need 5 of them, no problem. We'd look at that, see how much it weighs, and multiply it by 5. So after today, this gets real simple. But bear with me today because I do think it's useful to remember why that works. And why it works is an atomic mass unit is a measurement of weight, and a gram is a measurement of weight. So you can convert between them. And likewise, if every person weighs, if every person doesn't, but let's pretend every person weighs 200 grams or 200, what do I weigh? Let's say every person weighs 100 kilograms. I'm not quite 100 kilograms, but just to make it easy. If one person is 100 kilograms, right, then we'd know that if you got like 1,000 people, well, yeah, that would weigh 1,000 times 100 kilograms, right? That's one way to approach it. But the other thing to know is 1,000 kilograms is what we call a megagram. We never use that measurement, but it's real. So if you had 1,000 people, they would weigh 1,000 megagrams. Does that make sense? It converts. If we pick the right number, if it happens that 1 to 1,000 is also how you go from one weight to another, then you can just use the same number and change the unit. Does that kind of make sense? Let's say we did some math and we found that 1 penny weighed a gram. I have no idea if that's true or not, but does that make sense? Let's just pretend for the moment that 1 penny weighs 1 gram exactly. Can you imagine that? Well, how much does 1,000 grams equal? Well, 1,000 grams is 1 kilogram. Does that make sense? So then, if we had 1,000 pennies, yeah, we could say that equals 1,000 grams, but the other thing we could say is, oh, that's a kilogram. Does that make sense? You can just move the unit if we pick this number carefully, right? Does that kind of make sense? And so, if you're a place that like the mint where they make coins, I doubt you count out individual coins when you're sending them out. Maybe, I doubt it. Certainly, now maybe you can build a machine to count them, but in the past when you couldn't, I would bet you money that what they did was when they had to ship off, a certain amount of coins, they probably just weighed them, right? Does that make sense? And if you wanted to send them out in 1,000 at a time, You just, every time you get to a kilogram, put a box on it, and that's 1,000 pennies, and you don't ever have to actually count them. Does that make sense? You just know if one of them weighs a gram, then a kilogram must be 1,000 of them. Does that make sense? Well, that's all we're doing here, which is we know that if you have 6.02 times 10 to the 23rd atoms, which is a lot, then if those are hydrogen, they're going to weigh 1 gram because one of them weighs atomic mass unit. This many of them will weigh 1 gram. And if you have this many silicon atoms, well, since each one weighs 28 atomic mass units, this many of them will weigh 28 grams. We've picked a number that lets you go from one mass unit to another. All right, let's try talking about that. So how many atoms are there in 4.3 moles? You're all going to need a yellow calculator. So let me give you one. We're all going to need a yellow calculator because we're going to have to do some of that scientific notation nonsense, and we're going to do some dimensional analysis of math like we did yesterday. And again, I want you to bear with me and trust that, we're going to get through that all right. Okay. So we call that number a mole. 12 of something is a dozen. 20 of something is a score. 13 of something is a baker's dozen. If you have 6.02 times 10 to the 23rd of something, we call that a mole. I don't know why they picked mole. It seems like a stupid word, but here we are. Maybe short for molecule, maybe something like that, molecular. I don't know, but we call it a mole. And eventually you work with this long enough, it stops seeming like it's a stupid word to you, but it's pretty dumb, right? Anyway, let's get to it. So we want to know how many atoms do you have if you have 4.3 moles of carbon atoms. Again, we're only ever going to do this today because really, who cares? Does that make sense? Like, we know it's going to be some stupidly big number, right? But I just want to make sure this is something we can do so that times when it's useful to talk about that, we do it. Though again, today's work, not the most important work. But really, this is a unit conversion. So what do I have? I have 4.3 moles of carbon. So just like yesterday, we're going to write that down. We're going to say, okay, I have 4.3. And, moles is a lot of letters, right? Mole, M-O-L-E. So we give it a short form, which is obviously MOL. You might say that does not seem all that much shorter, and I would agree. But there you go. That's how we write moles. We say MOL. And a good idea to get in the habit is to subscript things. Even though it doesn't matter for this question, we're only talking about one thing by minute. So this is 4.3 moles. Moles of what? Moles of carbon. Remember, counting numbers have to be a thing, right? There's no such thing as just 2 dozen. That doesn't mean anything, but you can have 2 dozen cats, or you can have 2 dozen guitar strings, or you can have 2 dozen reasons why Orlando's class is the best class you'll ever take. Though you could probably have 500 dozen reasons why that's not true. Regardless, you have to count things. Does that make sense? So in this case, where are we counting? We're counting carbon atoms. How many do we have? We have 4.3 moles of them, which, by the way, just on the face of it is a lot, because how much is a mole? Well, it's this enormous number. And we have not just one of those big, enormous counts, but we have 4.3 of them. So much more than that, right? Way more. Just like 4 dozen is more than a dozen, 4.3 moles is that times 4, right? So now, you could just multiply this, right? But if you remember with dimensional analysis, we want to get in the habit of going slow when we go from one thing to another, because when we do difficult things, we want to be prepared for it. We want to be ready, right? So what I want you to do is first we write down what we already have. We write down the starting thing, the real thing in front of you. And then what do? We multiply by a fraction. Just multiply, put a line. And then what do we work with first? Units, never numbers, units. So what we're going to do here is we're going to say, okay, I've got 4.3 moles of carbon. I'm going to put a fraction. And on the bottom of that fraction, so it will divide away, so we can get rid of it, we put this same unit. We say, okay, I have 4.3 moles of carbon, but actually I don't want to know how many moles of carbon I have. Instead, up here, we put what we do want to know about, which in this case, they just want to know how many They want to know how many carbon atoms. So that's what we're going to put up here instead. We're just going to say atoms of carbon. And then we just have to know a true fact here. And by true fact, what I mean is we always put the relationship here. And in this case, it's a counting relationship. How much is 1 mole of something? Well, it's this big stupid number. What's the number again? 6.02 times 10 to the power of 23. Holy crap. Big number. And then we would just do this. And remember, this tells us that take 4.3, and then what do? We multiply it by 6.02 times 10 to the 23rd, and then what do? What does this line mean to do? We divide. So let's punch this into a calculator, and I'm going to very condescendingly write the buttons here, okay? So first we're going to put 4.3 in. So 4, then the decimal button, and then 3, and then we need to multiply, right? And then 6.02, so 6, and then decimal again, and then O, and then 2. And then the reason I'm doing this, should I press multiplication and then 1 0 next?
Press second and then press the comma, but...
Good. Yeah, good. Let me just pause there. Yes, this is multiplying, but scientific notation, your calculator, every good calculator has it built in. And on these calculators, how we get that is we press second function, and then we press the comma button, whose second function is this stupid double E. I don't know why they show it as a double E. Even worse, I don't know why they show it on the button as a double E, but then when you press it, it only puts a single E on the screen. That doesn't make any sense to me. That's not smart. But that button means times 10 to the exponent of. So what do I have to press after that? Well, I need to put the exponent in. And the exponent is 23, so I'm going to press a 2, then a 3, and I just keep going because the nice thing is your calculator will treat this as a single number. It doesn't treat it as something times something else. It treats it as a single number in scientific notation, which is really helpful. So always use this button. You will get the right answer if you multiply by 10 and put it to the exponent 23, but your calculator is then thinking of those as two numbers, and that will lead you sometimes to make mistakes because your calculator will do things in the wrong order for you. Does that make sense? And then I still have to keep going. In this case, it won't matter because what are we dividing by? But I'm still going to put in there, I'm going to divide, and then I'm going to press 1, and then your calculators have an enter button. And then when you do that, it's going to give you some big long stretch of decimals, and I bet I can actually guess them because let's see if I can do this. 6 times 4 is 24, 3 times 6 is, I can do this, 3 times 6 is 18, so this should be 25.8 something. Well, actually, your calculator is going to say 2.58, blah, 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 and at the end, it's going to say E24. Am I right about that?
Yes. You're just missing...
Yeah, a bunch of decimals there, right? What is this telling you? What does this mean? We already know what this means. This is the calculator's way of saying times 10. Yeah, and here's what it doesn't mean. It doesn't mean this number to the exponent 24. It means this number times 10 to the exponent of 24. In other words, this is your calculator's way of saying scientific notation. Are we allowed to write scientific notation like that? No. We are not. Now, we can round this number wherever we want. Do we have to put all the decimals they gave us in? No. Furthermore, how many decimals did I start with? Just, well, yeah, 2 numbers, just 1 decimal place, really. 2 here, but just 1 there. So let's just round this to the first decimal place. 2.58 should round to what? 2.58. 58, is that closer to 60 or closer to 50? 2.6. Yeah, so that's going to round to 2.6, right? 58 is closer to 60 than 50. And then instead of E24, what am I going to have to write? Times 10. Good. Does that make sense? So if I have 4.3 moles of carbon, if I told somebody to go count those atoms out, they would have to count 2.6 times 10 to the 24. And that, of course, is 2, and then 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. That's that many carbon atoms. Yeah. Oh, I love it. Come show me. Yeah, let's see. Let's see who got it. Who got it?
Unless we put it in wrong. If so, it was all his fault.
Nope, you got the same thing. Believe it or not, these are giving you the same answers. Your two calculators have different software installed, just different versions of the OS. And this one is rounding to the 3rd decimal place. So this is actually the same answer, but that, if you look here, slide over. But I'm glad you brought it. See how that's 2.58 and then 86, right? So 86. And this one isn't giving you that last decimal, so it's rounding. But 86, closer to 90 or closer to 80? 90. So if we were rounding this, it'd be 2.58890, which is what gives you here, right? 2.589. So no, same answer,
Okay.
but always bring things like that up. Does that make sense?
Yeah.
Yeah, good. Very good. Yeah.
Just for curiosity, how many atoms are in the entire universe?
That is not just curiosity. That's a very good question. I'm going to run out of time today if I answer it, but I will talk to you tomorrow about it because it's actually one of those great back of the napkin kind of things. Scientists have roughly an answer, which is to say they don't know the number, but they think they know what the times 10, they think they know what this roughly is, which is as close as we can get, right? We're not going to get the exact number here. Okay, let's try another one. This time we're going the other way. I'm starting with atoms. How many atoms? Lots. Hey, before we even do it, is this 4.55 times 10 to the 24? How much is a mole again? 6.02 times 10 to the 23. So is this bigger than a mole or smaller than a mole? Bigger, right? Roughly, the nice thing is when you use scientific notation, every time the exponent goes up by 1, that's about 10 times bigger. Does that make sense? So this is roughly 10 times bigger than a mole. It won't be exactly 10 times bigger because these two numbers are different. Does that make sense? But this is about 10 times bigger. Does that make sense? That's the nice thing about scientific notation. If this was 26, you could say, okay, 23, 24, 25, 26. Oh, that's 1 and 3 zeros. That's about 1,000 times bigger. Does that make sense? So scientific notation actually lets us kind of eyeball numbers really quickly. So when you get, at first it seems confusing, and with a bit of practice, it often, if you're a physics guy who's just quickly working something out, you might not even use these numbers at all. You might just look at the exponents and figure out roughly what your answer is and go from there. Anyway, 10 to the 24 atoms. And again, we're doing scientific notation. When I do, we're doing what we call dimensional analysis, which is we're going to work with multiplying by fractions to get our answer. To do that, every time, what do? I write down what I have, and then I multiply by what? A fraction. What don't I put in first? Our temptation is to start putting numbers in there, but I actually don't put numbers in yet. What do I put?
You put in the measurement of the unit.
We look at the unit. So the first thing is always, what unit do I not want to talk about anymore? Well, it gave me atoms, and it's asking me instead for how many moles that is. So we want to get rid of atoms. So where does it go? On the bottom. No numbers yet, just units. Instead of atoms, what do I want to talk about? Moles. That goes on top. No numbers yet. And then this fraction never has anything to do with your question. Does that make sense? You're not grabbing the numbers from your question for this. These fractions always just have to be facts. They just have to be true. You have to know what the relationship between these two things is. And as it happens, we know that 1 mole is the same thing as, just like 1 dozen is the same as 12 of that thing. In this case, 1 mole is the same of atoms.
I don't like 1 moles.
You're right. That should say 1 mole, really, right? This is the problem where, because what I would really do is I'd use the short form and then it's never pluralized. But you're right. 1 mole is the same as how many atoms? How many atoms in a mole? How many anything in a mole of that thing? 6.02 times 10 to the 23rd. And now here is a perfect example where if you use the scientific notation button on this, you'll get the right answer. If you use the multiplication button and put 10 to the 23rd in it, you'll get the wrong answer. So we're going to use, because you'd have to put brackets around it, which we don't want to have to do. So this is an example of where we're going to use the scientific notation button. So try it. I will put the instructions after, but try it on your own first. How many times are you going to have to use the scientific notation button to do this one? Twice, right? Because we have this number in scientific notation and that one. By the way, we take this number and what do we do with it? We take that number and we times it by 1. And then we take, and all in the same calculation. Don't press equals. Then after multiplying it by 1, we're going to divide it by that. All right, try that out.
Can I yell it out loud?
No. No, give people a map. 9 twelfths, 9 twelfths. What's 9 twelfths? 9 twelfths, 9 twelfths. One sec. 9 elevenths would be 0.88. 9 twelfths is going to be less than that. I think it's going to be 8 point. Okay, let's see if I can do this. I'm going to guess, and you guys are going to tell me if I'm right. Give me a sec. 8 point. No? No? What'd you get?
I got 7.558.
Damn it. Oh, right. Yeah, I was thinking wrong. I went up when I should have gone down. I'm so ashamed. Are you ashamed of me?
No.
I used to work in a fish market,
I don't care.
and I worked in the fish market. We had a scale that would like weigh the fillets, and then it would print a label that you'd put on, like, you know, like when you go to the grocery store and they weigh something out and it prints the label and they scan it at the cash. But it was just a barcode. There were no numbers on it, and my scale would tell me the weight but not the price. But I knew that like a salmon fillet was $8 a pound. So and so my goal would always be, by the time I got to the cash register, to have what it would cost them in my head. So I'd always, and like if it was an order of like some salmon and some haddock and like a couple of shrimp, I'd be like in my head doing it, and I would always try. And if I was confident, I'd even say the price before I got over and scanned it. And if I was right, I'd feel real smug. And if I was wrong, I'd feel really stupid. And this is a useless skill. Like, I want to be clear. This is not like bragging. This is me reflecting on why girls didn't like me in high school. But yeah, I always like tried to hone my mental math skills.
No one likes me.
Sorry?
No one likes me.
There's no way that's true. You know, I discovered like in adulthood that actually it turns out like there were girls who did like me, and I was blissfully unaware of these things. So what you might find is that developing some confidence is useful, but that's something I haven't figured out yet. But I'm confident that one of these days I'll be confident. Anyway, yeah.
Is there a different way to set up this equation thingy?
No, I mean, there's a million ways to set up, but I want you to do it this way, and you're going to see why. I know this seems overcomplicated. But you're going to have to trust me that when we get to difficult stuff, this is going to change your life. It's going to be way better. So bear with me. All right. So how do we punch this into our calculator? Well, we have to put this number in, which is 4.55. I'm not going to bother drawing each button. But then what buttons do I press to get the scientific notation? Second and comma, right? And then we can say 24, right? Then we press that multiplication button, and then we do 6.02. Or sorry, no, we're not multiplying by 6.02. Where are we multiplying by? 1. Then what do? Then we're dividing. Then 6.02, and then how do we get scientific notation? Second function, and then comma, and then 23, and then enter, right? And when we do that, we got what? 8.7 point, did again, 7.5?
7.6 it should be.
There we go, because it rounds to that, right? And what's our unit? We never want to lose our unit. It was atoms, but we divided atoms away. Those cancel each other out. So the unit we're left with is moles. And now that it's more than one, we'll put an S on it. Though really what we do is we just say MOL for mole.
Because I remember you saying, like, if it makes sense in your head, then, like, it should be right.
That's right.
But, like, if you use, you know, like, wrong.
Yeah, it's helpful because, yeah, if you put that S, again, usually we just use the short form. Okay. This is just more of the same. All right? It's just more of the same. We'll do one more together. But the main thing I want to stress with you is this. This is actually the worst version of this, because these big numbers don't mean anything to us, right? They're so big that they're just big, stupid numbers. Does that make sense? They're completely unfeasible. They're intangible, right? They are esoteric. Do you know the word esoteric?
No.
Esoteric means like obscure. Something that is esoteric is like something that not a lot of people have heard of, and it sounds strange and foreign to you. Not unlike the word esoteric. It is a word that describes itself, which is kind of interesting.
Like
And esoterica is like a collection of things. But anytime you deal with something that is like hard to picture, I can't imagine something harder to picture than that number. It just doesn't mean anything. So I can't stress enough, you have to do this day, or we have to do the day where we talk about counting atoms. It's just the single most useless day here. Tomorrow we're going to say, great, now let's shove all that in the back and let's actually do real chemistry where we immediately stop talking about these numbers at all and we jump right to working with masses, things we can actually go in the back and weigh out. And especially, you guys are in a college chemistry class. And college is not about esoterica, all right? The place for esoterica is university. And I went to university, I liked it, but it really is, university is the place where you go to sit around and talk about stuff. And some people really like that. Perhaps you've noticed about me that I'm somebody who likes to sit around and talk. I mean, subtle. You may have missed that. Who was giving me a hard time today for getting distracted and turning around and immediately carrying on yet another conversation? But on the other hand, you know where we go to learn practical skills? Well, we go to college, we go to the trades, and we go to work, right? Where they really mostly don't care about this stuff. You know how many guys you need in a biochem lab who understands all of the concepts? I don't know, 1 or 2. You know how many people you need who can do the job? Lots. Even you go to a hospital, you've got scientists who do the research that publish it. You need a few of those, right? They work stuff out, but mostly you need doctors. And doctors have a little bit of this, but more of that. Doctor, for all we think of them as like kind of nerdy, brainy people, it's mostly a technical job. They're basically body mechanics, right? They fix your body, mechanic fixes your car, right? You need some scientists to figure things out. You need doctors who do a bit of this, but mostly that. And then, what are there way more of than doctors? You go to the hospital, you might see the doctor for 2 minutes. Who do you see mostly? Nurses, orderlies, right? And they are focused on this practical stuff. Does that make sense? What I love about this college chemistry class is that we touch on this stuff, all right? The truth is, you're doing every bit as much of this as the university chem guys. But the real truth is, I've made the 3U chem here more of this stuff. Our university chem kids do as many labs as you guys do. And you guys do more labs than any other high school is doing in chemistry. Trust me, I've asked around. And we're dragging the U kids along to try to give you some practical experience. Do you know why we're doing that? Because you know where there's way more jobs in science?
Hands-on.
Way more. Again, how many research scientists are there, especially in Canada, where we've just decided that, we don't want to spend tax money on scientific research? There's not all that many jobs in research. But you know what happens every time you go get blood work done? They take your blood and you know what they send it off to? Send it off to a lab. And you know what happens in that lab?
Hands-on stuff.
Hands-on stuff. They put it in test tubes, they spin it down, and they repeat those skills. Does that make sense? And don't get me wrong, people who work in labs are smart people. Do they understand a bit of this stuff? Of course they do. They went to school for it. They know what they're doing, just like you guys are going to understand all this stuff too. But this isn't their focus. Their focus is the skill, is the actual doing of the thing. And you ask any doctor who's honest, and they'll tell you they can't do the physical skill stuff that most nurses do at the same level they do, right? And the doctors who get paid the most, which doctors get paid the most? Yeah. Who? Surgeons. It's not the family doc who has to know a little bit about everything because you're coming in and saying, hey, I'm coughing funny and my knee's bent 30 degrees to the left, and they have to figure out what that means. The doctor who gets paid the most is the one who has the most amazingly difficult practical skill. You ever watched a surgeon at work? I was lucky. When I went to university, I thought for a while I wanted to be a doctor. Turns out I'm too stupid. And I was part of a program called Med Plus, and I got to shadow surgery. And I got to watch a doctor actually do surgery, and you're like, it's unbelievable that people can do this, the fine motor skills. My wife had thyroid cancer, and she had to have her thyroid removed. This was 2009. So in 2009, she was pretty young. How old would my wife have been? 26. She's 26. It was scary. We had little kids. And so you know where your thyroid is? Ready? Take 2 fingers. If you can feel your Adam's apple, kind of feel under it and palpate your trachea. That's like your windpipe. And if you palpate along there, not up where your Adam's apple is, that's a different structure. That's called your larynx. That's your voice box. But underneath that, you'll feel like some soft tissue. That is your thank you. I don't know why I just lost the word. Oh, I do. My brain is foggy. So she had to have that taken out because it was covered in tumors. So think that's on your neck, right? So the surgeon had to cut open her neck and fold the tissue back. Now, I wasn't in there for this one. I was in the waiting room freaking out because I'm a nervous Nelly. And He opened it up, and he did. He took it out, and then he sewed her back up. And when she came out of that surgery, it looked like a slasher film. She had like Frankenstein-style stitches all the way along here. Now, they would probably do a glue joint on that and do a much smaller cut, because laparoscopic surgeries where they go in with like kind of finer tools have become more common. Yeah, at the time, I thought, oh my God, she looks like a murderer. It was horrifying. To say nothing of the fact that like then, 3 weeks later when she was back on her feet and we were like going out and about, you go out with her and like, don't mind me, just with my wife who has her throat slashed, was awkward. But here's the crazy thing. That guy put the incision right along one of the natural folds of your neck. You know, you lean down, you lean up, and you have some little wrinkles on there. And by the time that scar healed, invisible. Completely invisible. You cannot see it. If she kind of stretches the skin of her neck up, you can see like, oh, there's a scar there. But just in her day-to-day life, you would never know. And again, like when it was done, the skill and the precision. So I can't stress enough, if this stuff, working with these kind of numbers, makes you think like, oh my God, what am I doing? This lesson today, it's going to be like probably 5% of this unit test. It'll be like 1% of your final exam. And it really and truly doesn't matter. Does that make sense? This math skill matters, though. Learning how to work with what we call dimensional analysis, canceling units using these fractions, that's going to be super useful. When we get going tomorrow, we're saying, okay, enough theory. Let's talk about actually working in the lab. That's where it picks up and starts being really important. Okay, so if this today feels like, what are all these numbers? Why is there scientific notation? What does it even mean to have 6 with 23 zeros after it of something? Don't worry about it. Really isn't that important. All right, I want you to do it. I want you to do your best with it. But for a lot of kids, they see this and they kind of shut down. Just who cares? If you see this and shut down, great. See this and shut down. Just make sure you pay attention tomorrow, because that one's the actual practical skill we're going to use. On the other hand, I find this really interesting. I think the math of it's neat, but it's not that important. Okay, if we have 3.12 times 10 to the negative 3 moles of iron. First of all, if I wanted to write that as a normal number, would it be horrible, or is that a number that could actually be an okay little normal number? 3.12, but then this...
Okay.
Yeah, is this a big number or a small number?
Small.
Yeah, it's not like super small, but small, right? Which means the decimal's going which way? This way? Does that make it smaller? No, that makes it bigger. So the decimal's going this way. How many times? 3 times. So we can move it once, twice, 3 times. Now the decimal's there. Oh no, we have empty spaces. Okay, so a 0 and a 0. And what would we usually put here as well? Just manners. So that's that number in standard notation. If you'd rather work with that, I think I would. So I'm actually not going to work with that. I'm just going to say 0.00312. I don't think that one needs scientific notation. I think that's probably easier. Does that make sense? If you want to work with scientific notation, that's fine. And what is that? Because we always put units down. That is 3.12 times 10 to the negative 3. What's the symbol for moles? Gotta save that space. MOL. Oh, that's so efficient. And then it's moles of iron. What's the symbol for iron? Fe. See that kind of habit? The unit and the subscript tells us what we're talking about. Okay, and then with dimensional analysis, what do I do every time? Multiply by a fraction. What do we do next? Do we talk about numbers? Do I start putting numbers in here?
You talk about the measurements.
We talk about the units, the measurements. Good. In this case, do I want to talk about moles anymore? No, and it's always going to go on the bottom. And the reason it goes on the bottom is because we're going to divide. And when you divide something by itself, it goes away. Anything divided by itself just disappears. So we're going to make the unit we don't want to talk about disappear mathematically. And we're going to replace it with the unit we do want to talk about, which in this case is atoms. Okay. And again, atoms of iron. I'm going to get in the habit of putting those little subscripts so I know what we're talking about. It's not important now, but when we get to more complicated things, keeping track of what you're talking about becomes important. And now we need to know the relationship. Is one atom 6.02 times 10 to the 23 moles? If I put those numbers there, does that make sense? Say it out loud. Oh yeah, 6.02 times 10 to the 23 moles of atoms, groups of atoms, is one atom. No, that doesn't make sense.
What?
That doesn't make sense. So the number goes here. 6.02 times 10 to the 23rd of anything is 1 mole of that thing. And that's our setup. And then what units will cancel? Well, moles is going to divide by moles, and the unit we'll be left with is atoms. And again, if you I know the dimensional analysis seems sometimes like a confusing waste of time, but trust me, If you saw the equations they use when they teach chemistry by equation, you'd have a formula sheet with like 15 formulas on it. Instead, we're going to do the whole course just doing this all the time. The same thing every question. And once you get good at it, it's going to change your life. All right, make sure you put this into your calculator well. 3 times 6 is 18. So that's going to be 18 point, and then 6, but then 2 times 6, that's going to be 18.72. But then we're going to move that back, so it's going to be 1.872 times 10 to the, that'd be 23, 22, 21, 20. But then back up, it's 21. How'd I do? How'd I do?
Awesome.
Did I get it?
Yeah.
Did I nail it?
Yeah.
Hey! And then we don't actually want all these decimal places.
Well, I mean, it would be 1.9.
I'm going to round to 1.87 because we had 3 numbers here. We could round to 1.9. I don't care which. Does that make sense?
Yeah.
Again, we'll do a day on rounding. For now, I don't really care. Did I get it? I'm so proud of myself. Take that, Fine Kettle of Fish, Fish Market. And that's the skill there. There's a few more practice questions. I do want you to try them, but I don't want you to stress about this stuff. I really can't stress that enough. The biggest takeaway today is this. The big thing I want you to take away is that what we really care about is the fact that with this stupid number, it lets us convert from a unit that is useless to us, which is atomic mass units, and turn it into a unit that's really useful to us, grams. Does that make sense? That's what I actually care about. The rest of it, counting atoms is a waste of time. Now, like a lot of things are a waste of time, I'm still going to make you do it. But I'm not stressed about it. Yeah, we'll call it there.